Hello, my name is Matt and I'm a double degree student in engineering and science, and I've chosen to do my FYP in a physics lab that works with these really cold atoms called Bose-Einstein condensates. Now, the point of the lab is to actually be able to measure magnetic fields in the air and around us, useful things. And what I've been doing is actually designing some of the hardware that will go into this lab to be able to process the signals that come off these cold atoms. So I've been working primarily with an FPGA, an Altera FPGA, and designing a heap of hardware in HDL, which is hardware design language. In addition to that, I also designed a printed circuit board for a differential amplifier, a dual channel differential amplifier, and that serves the function of actually taking the output from these digital to analog converters here and making it ready for the lab. I hope you enjoy this video.
In the BEC apparatus, we make clouds of very cold atoms. These atoms can be thought of like little classical magnets. However, they don't exhibit a classical spectrum. So, if I was to have a little bar magnet and put it in a field, based on its orientation I could tell you how much it'd be pushed or repelled. Instead, for these atoms, they only exhibit a discrete orientation as little bar magnets. And as a result, we can actually use population statistics to be able to measure the magnetic fields affecting these atoms. Some of the applications that we want to be able to use these cold atoms for are actually detecting real-world events occurring. An example might be a neuron firing that gives off a magnetic signal as the chemical gradient changes down the axion. And another example might be a drone up in the sky. It's got little motors in it that spin around at some frequency. And that gives off a magnetic field as well. And ideally we'd be able to actually detect something like that quite sensitively. The cold atoms are state prepared into something called dress states by using the magnetic coils around the atoms. A laser is then used to make a Faraday measurement. This is basically imprinting the magnetic state of the atoms onto the phase of the light. By using optical polarizers in conjunction with photodiodes, we can make an electronic measurement of the phase of the light and hence the magnetic fields affecting the atoms. Because of our state preparation, our electronic signal is actually rather complex. It roughly looks something like this: a waveform with a carrier frequency, amplitude modulated. It also has in-phase and quadrature information that is sensitive and needs to be decoded. The real signal will also be covered in a fair amount of photon shot noise, something that comes from the photodiodes. And this is where my project comes into the lab. In the past, they used to record data and analyze it maybe up to 10 seconds after the actual event had happened. To do this, they'd do Fourier analysis and be able to create spectrograms detailing what frequencies were actually present in their system. Instead, what we want to focus on in this project is actually making these sorts of processes real time. This is important because it means that we can actually detect things that are happening live, and we can also give instantaneous feedback to the atoms or the coils or anything that we want to be able to control in the future. Another focus of this project is to be able to do multiple channel analysis in parallel at the same time. Instead of buying a pre-made unit off the shelf, they can only probably do one channel and probably cost a lot of money. What we actually want to develop is something that can actually do multiple channels at once, and hence lets us listen at many different frequencies to the atoms. In terms of the requirements for this project, we require ability to be able to demodulate carrier frequencies of 300 kHz up to about 3 MHz. This is the current operating frequencies of the lab, to the points of which we can actually use the photodiodes to be able to receive particular frequencies. We need to be able to demodulate amplitude modulation on top of this, from anywhere from 1 kHz through to 100 kHz. And we need to have under 100 microseconds delay. Usually this AM information is maybe about 10 kHz sort of size, and as a result 100 microseconds is about 10 cycles or 10 periods of that frequency. So we want to be able to respond fairly fast to whatever the frequencies are that are occurring. We require at least 12 bits of dynamic resolution, and that's because there's a fair amount of noise actually that covers our signal, and some of the lower magnitude signals or weaker signals will actually appear as very small magnitudes. And lastly, we also need to be able to demodulate in-phase and quadrature channels. So data comes through through the photodiodes on 2 different phases, and we need both of these phases to properly reconstruct what is happening. We decided to implement the system on a field programmable gate array, or an FPGA, in conjunction with the Thoracic ADDA daughter board, which allows for analog to digital and digital to analog conversion. The reason for using an FPGA is because it's easily reconfigurable for our needs, and we don't have to print off a new circuit board each time we want to design the next component. This allows us to actually pipeline our hardware in logic, and it actually allows us to estimate our latency very easily. The FPGA that we've used is an Altera FPGA, Cyclone 5 SoC. It actually has a fair amount of memory, which is quite useful for things like filters and filter design, which has to store coefficients. In addition to this, our FPGA actually operates at a 50 megahertz clock rate, which is ample for being able to sample a 3 megahertz carrier wave. The Thoracic daughter card itself has 14 bits of resolution, and so satisfies our 12-bit resolution requirement. It also clocks up to about 65 megahertz sampling rate and about 100 megahertz output rate. The unfortunate thing about this card is that it actually has a couple of transformers on its inputs and outputs. This isn't helpful for us because we actually want to be able to demodulate a signal which is fairly slow, and these transformers actually restrict our frequency range into high AC. To overcome this issue, we actually removed these transformers and created single-ended outputs until we actually designed a printed circuit board, and I'll discuss this later on in this video. So what did we actually design in HDL to be able to achieve our goals? This here is a block diagram, and it shows the little components that we actually designed in HDL to be able to synthesize onto the FPGA and get it to actually run the circuit that we need to run. The first block that you can see there is an unsigned to signed conversion unit, and that was necessary because the digital to analog converter itself only took in 1 sign of data, whereas the data that we were actually providing it through the transformer was actually an AC, which centered around 0. The next block that was implemented is the IQ module, and this contains a heap of subcomponents. First up is the numerically controlled oscillator. This is something that generates a cos wave or a sine wave, and lets you actually be able to generate any particular frequency you like. We actually use this to match the carrier frequency, and we can specify it by running the numerically controlled oscillator off the board's frequency, the 50 megahertz, and then actually specifying a phase incrementer. And this phase incrementer, which is 32 bits long, allows you to actually be able to accurately simulate any frequency smaller than the 50 megahertz itself. The next element in the block diagram is the multiplier, and this is where a lot of the magic actually happens. So in a multiplier, what we do is we actually mix 2 different frequencies together, and what this will do is actually cause a frequency that has the addition of the frequencies and the subtraction of the frequencies. When our numerically controlled oscillator runs at the same frequency as the carrier frequency, we get a signal that's actually then just DC, so one that's at 0 Hz, and another signal that's actually twice the carrier frequency. The important thing to note here is that the output, both the DC as well as the doubled carrier frequency, actually still contain the amplitude data on the original input signal. When there's amplitude modulation on top of a DC signal, this is actually something that just gives you the signal back at some offset, some DC offset. This is why this signal is very useful for us, and why we actually don't care so much about the signal with the double carrier frequency. It's actually in our interests at this point to filter out this higher frequency that we don't want anymore, and just retain the information on the DC signal. And so what we actually implement next is an FIR filter, and this is a finite impulse response filter. How it works is it takes input samples and buffers them. Then, by using a set of stored coefficients in memory, it actually multiplies each of these buffered values and adds them together to give you a result. Doing this and being able to tune these coefficients in a certain way actually allows you to filter out certain frequencies of data that are running through your system and cancel them out while allowing other things to pass through. We used the filter compilers in MATLAB to be able to design our filter. In particular, we used the function FIRGR, which generates a generalized Remez FIR filter. This here is an example of one of our previous filter designs, but it wasn't sharp enough for our desired purposes. As you can see, as we slowly increase our numerically controlled oscillator frequency, splitting occurs, one that's plus and one that's minus from the carrier point. As the larger frequency increases, you can see it start to drop off and roll off with attenuation because of the filter that we've designed, whereas the frequency going towards DC actually becomes stronger and stronger as desired. The filter that we have designed actually operates at a sampling frequency of 12.5 MHz. It's limited to 120 coefficients, which also correspond to 120 clock samples, and has a passage of 10 kHz. We also let the stop band ripple about 3 dB and had a stop band attenuation of 40 decibels. The stop band frequency that we desired to actually filter out down to at 40 decibels was 300 kHz. And this is because our carrier frequency is at 300 kHz and above. So if we're mixing by that frequency, then we should actually expect things at around 600 kHz as a minimum. Lastly, to be able to output onto the digital to analog converters of the DAC, we need to be able to convert from the signed representation back into the unsigned or the binary that the DACs take. And we write another module to be able to do that. For a few of the blocks in the last module diagram, we used some of Quartus's native megafunction tools to be able to generate some of the code. In particular, we used the FIR2 compiler, the NCO module, as well as the LPM multiplier megafunction wizards to be able to design and to synthesize our desired blocks. Building from this, we implemented multiple of these IQ modules, putting all these things together. And this is actually where we ran into an optimization problem. As we wanted to increase the amount of IQ modules that we were implementing, we also realized that we were starting to run out of resources. A large contribution to this were the 3 megafunctions that we were using. To actually be able to achieve our current result of 3 IQ modules in parallel, we actually needed to be able to remove some of the other logic that we'd incorporated for extra functionality. This included a hex display module, which outputted the frequency being generated by each oscillator, as well as both a reference locking frequency that we were generating and phase correctors in each module, which reduced the frequency error of the 50 MHz clock on the board. Another option instead of removing these elements was actually to decrease our filter size and hence use less coefficients. This would free up resources as well. Having these two things is actually a useful option, as this actually allows us to customize functionality in the future to be able to choose what things are more important for the lab work. Another significant contribution that was made was generating this dual channel differential amplifier. It was necessary because we actually had DC offputs on our single-ended outputs from the ADDA daughter card. For integration into the lab, the signal needed to be amplified a little bit, but also needed to be centered around 0. This differential amplifier was designed to be plugged in to where the ports were for the old transformers that we removed from the original daughter ADDA card. Through a simplification of RF being equal to RG and RB equal to RA, we can actually have a very simple gain equation for this circuit. The values that we chose for our resistors were 2.5 kiloohms for RG or RF and 511 ohms for RA or RB. During routing, care was taken to make sure pathing was as linear or as rounded as it could be. Bypass capacitors were also added onto the power rails to filter out common mode errors or surges. Although not included in this design, reconstruction capacitors were also put in parallel across RF1 and RF2. This serves the purpose of acting as a low-pass filter for any ultra-high frequencies that we shouldn't be expecting from the outputs. So we've got to show our system is actually working right. These 4 videos will show you the operational ability of our FPGA circuit and differential amplifier. In the bottom right, you can see an external frequency in the blue being mixed by our internal IQ module, resulting in the yellow output. As we increase the frequency, it'll come towards 1 MHz and actually mix appropriately and then fall back off. On the bottom left, we show an amplitude modulated carrier signal. As we increase the frequency of the carrier, it begins to mix with the internal oscillator at a correct frequency, and a signal appears that's AM demodulated. On the top left, we show this same thing, but with the I and Q channels. We also switch between an AM modulated signal and just a straight carrier signal in this example. In the top right, we show the operational ability of our differential amplifier. One of the signals is the single-ended output from the DAC, and the other one is the amplified signal. Overall, I feel this has been a very successful project in which I've learned a lot of physics at the same time as actually being able to put my engineering skills to use. I also want to take this opportunity to thank both my supervisors, Lincoln Turner and James Saunderson, for their help and supervision during this year-long project. And yeah, thank my lab group as well, and feel free to hit me up if you've got any questions or are interested. Thanks.